Newton's second law states that the acceleration of an object is proportional to the resultant force acting on it and inversely proportional to its mass. This is the second of Newton's 3 laws which you may be asked to state in an exam. The key to this law is the term proportionality. When 2 quantities are proportional, doubling one will double the other. When 2 quantities are inversely proportional, doubling one will halve the other. Let's see how this law works with an example of a cyclist. There'll be 2 forces acting here. The forward driving force from the cyclist pedalling and the backward frictional force from the road. Remember that the resultant force will be the vector sum of these forces, or the single force which has the same effect as these combined. As the driving force is stronger, the resultant force will also be directed forwards. But how does this affect the acceleration, the vector quantity that tells us how motion is changing? Well, when 2 vectors are proportional to each other, they have to be in the same direction. So we can draw an acceleration vector in the same direction as the resultant force. The proportionality relation also tells us that if we increase this resultant force, such as by applying a stronger driving force, the acceleration will also increase. More precisely, if we doubled the resultant force, then the acceleration will also double. But why is it important that we know the direction of the resultant force and the acceleration? Well, if the resultant force is in the direction of motion, the object will gain speed. Let's consider this example of a falling skydiver. As they are falling downwards, we say that they have a downward velocity. Remember that velocity is also a vector. It tells us an object's speed and the direction they're travelling in. The skydiver experiences a downward weight and an upward drag, but the weight is stronger, so there is a downward resultant force. Since the resultant force, and hence acceleration, is in the same direction as velocity, the speed increases. But what if the resultant force was in the opposite direction? If the resultant force is opposite to the direction of motion, the object will lose speed. Let's go back to our skydiver, but now they've opened their parachute. They still have a downward velocity, but opening the parachute greatly increases the upward drag force acting on them. This means the drag is now greater than the weight, so the resultant force will be directed upwards. Now, the resultant force and the acceleration are in the opposite direction to velocity. This means the parachutist loses speed as the resultant force opposes their motion. But what if the resultant force is in a different direction than it was in these 2 examples? Well, if the resultant force is not aligned with the direction of motion, then the object will change direction. By not aligned, we mean it's neither in the same or opposite direction to the velocity. It will be somewhere in between. For example, let's suppose we have a ball travelling through the air, and its velocity is in this direction, parallel to the ground. The only force acting on the ball is its weight, so we'll have a downward resultant force. Notice that it's at right angles to the velocity. Now, what would the effect of this perpendicular resultant be? Well, we'll see the path of the ball curve as the force causes it to curve downwards instead of continue on straight. The speed might not necessarily change, but as the direction changes, we'll still see an acceleration causing a change in velocity. So that's how forces affect accelerations. But what about mass? When 2 objects experience the same resultant force, the object with greater mass will experience less acceleration. Now, this should be quite obvious. It's why we have difficulty moving heavy objects around. We have to apply much greater forces to get the accelerations we need. Let's see how this works by looking at a sports car and a truck, where the truck has a much larger mass. Let's suppose that both experience the same resultant force. Now, if we were to measure the acceleration of the 2 vehicles, we'd find that the truck has a much smaller acceleration compared to the sports car. This is because the truck has a larger mass, and Newton's second law states that acceleration is inversely proportional to mass. If we want the truck to have the same acceleration as a sports car, we'd have to use a much greater driving force. You need to be comfortable explaining how Newton's second law applies to a variety of contexts and predict what will happen when the resultant force is changed. But what would happen if there wasn't actually a resultant force? Do we know this answer already? Well, Newton's first law can be thought of as a special case of Newton's second law when the resultant force is zero. Remember that Newton's first law states that when the resultant force on an object is zero, it will either stay at rest or move with constant velocity. Let's look at an example of someone on a mobility scooter. They have a driving force of 100 newtons and a resistive force of 100 newtons. Since both forces are equal and opposite, they cancel each other out and the resultant force is zero. Now, Newton's second law tells us that the acceleration is proportional to this resultant force. If the resultant force is zero, then the acceleration must also be zero. But what exactly does this mean? Well, if acceleration is a measure of how velocity changes, then an acceleration of zero means there is no change in velocity. This is what Newton's first law predicted, and we've shown that we can reach the same conclusion using Newton's second law. You'll need to be able to explain this link between the two laws for your exam.
Thanks for watching. If you want to take your GCSE revision to the next level, head over to launchpadlearning.com and check out our smart learning platform that's been designed to get you top results in your exams. We cover your whole specification and make revision fun with interactive quizzes, easy-to-follow videos, and more. You'll be kept motivated by your own AI tutor who's here to support you every step of the way. To check it out for yourself, click here. Or click here to keep watching a selection of the videos from our full GCSE Physics course. See you there!